So the last session in this part on differential equations is going to talk about numerical schemes. Okay, and this subject by itself, numerical schemes for differential equations, is a broad subject by itself. You have books, monographs, textbooks, monographs, whatever written on this subject, and so to have any hope of covering it in a single session is kind of fanciful. So I won't necessarily be able to do much, but the motivation for today's session is going to be kind of short for that reason. The motivation is to basically give you some idea of the type of steps involved when you want to do numerical solutions for differential equations. And you will see that the same type of ideas in a slightly more sophisticated form will carry through if you look at PDEs at some point, okay, which many of you I'm sure will do. So in that sense, this will set the groundwork a little bit. It will give you some familiarity with some of the terms, of course not all of them, and it will sort of put you in a mode in which you will think a little bit carefully before you make some approximations. Okay, that's the whole point of the scheme. Now, having said that, the distinction between initial value problems and boundary value problems that started becoming quite apparent last time, not just from the point of view of a solution of a differential equation, but from a point of view of things like eigenvalues and special functions and things like that. Boundary value problems are a little bit more can be a little bit more complicated, so they need a few more special techniques, and the same principle applies to numerical schemes as well. So numerical schemes for boundary value problems are a little bit more complicated than numerical schemes for initial value problems, and the reason excuse me should be clear. It basically is in the way in which the problem is specified. So you need some guesswork, you need some a priori information to solve a boundary value problem using numerical schemes. So what we'll do today is we'll focus on initial value problems. Okay, and like I said, it's going to be reasonably short. So in the short time that we have, we'll do the following. We'll see standard, sort of loosely standard procedure for approaching any initial value problem. Now, many of you have probably done at some point some finite difference type scheme for an ODE, often naively without realizing what the error is or without keeping track of how much error you're introducing and things like that. But it has to be done systematically, because as we'll see, if you just do simple forward difference, the scheme need not be stable. So there's something called numerical stability. We'll talk about that. So this is different from stability of the differential equation itself. Stability of differential equation we know how to evaluate. So it's okay, shouldn't say stability of differential equation, stability of a fixed point in the differential equation we know how to evaluate by doing linearization and the usual stuff. And in addition, when you do a numerical scheme, the scheme itself has to be stable. So it shouldn't introduce errors at every step which keep adding up. Okay, so by definition, the fact that you're making an approximation to a differential equation means that you're introducing some error at every step, and if these errors start accumulating in a sort of unbounded way, then the scheme is not going to be stable. Okay, so we'll see there are three types of stability that you can find here. The criteria for determining stability is are quite complicated, and they depend usually on the differential equations that you have in mind that you're actually trying to solve. So we won't get into too many details. I'll tell you what they are, so that when you see these terms eventually you will be able to relate to them. And we'll then mention a few things in closure about where all of this will fit in and so on. Okay, and this will be the end of this entire 10 or 11 session bit on differential equations. So we'll be concluding and bringing stuff to closure today, and hopefully you would have had a good idea of what differential equations entail, not just at the undergraduate level, but something a little bit more deep, I hope, and something a little bit more revealing, hopefully. So anyway, okay. So let's start with the standard procedure first. So let's say I have a differential equation that looks like this. I have an initial value problem that looks like this. Equals y naught, and then I'm going to say 0 less than t less than some capital T, doesn't matter. Okay, capital T can be infinity, but okay, we'll take some number so that it makes it easier for us to approximate. And you also have to take some number because you can't in principle solve for small t going to infinity in a numerical scheme. You have to stop it somewhere, so we'll set that somewhere to be capital T. Okay, this is an initial value problem, 1D, so 1D differential equation, generally non-linear. It can be non-autonomous, it is whatever, non-homogeneous, all of those things, all of those good things. So we look at this as a prototypical example, okay, 1D system. Why are we interested in this? Well, you can take any, remember, you can take any higher order system and write it off in this form. We've seen that before. Okay, so you can write any higher order system, non-linear system in general in that form, where f is a vector that contains entries as rows, whatever, which contain f1, f2, f3 if you have many of these, and y will be dy by dt will be dy1, dy2, dy3, whatever. Okay, the usual stuff. So whatever we say here can directly be translated over here most of the time. So at least whatever we are going to say will be translatable. In general, these ideas will also be translatable, except for a few caveats. You have to be careful, but okay, we'll not worry about that. Okay, so what are the 5 steps that you have to do? First, you have to write, if you're going to solve this on a computer, you need to pick t values, let's say time t values. We denote them by ti is equal to I times h. Okay, the ith ti is I times h. H is t by, let's say, capital M. I have m points. Actually, m plus 1 points including 0, but okay, let's say m. So I start from here. Let's say this is 0, this is capital T. I break it up. Here I've taken equal intervals, you don't have to, but okay, here I have. And we'll talk about the non-equal maybe a little later on. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 points. So m is 10 here, 10 points. And this fellow is h. Okay. And this is T1, T2, T3, Tm. Okay, m is 9 here. Okay, whatever. M is 9. Okay. So if I do this, then that's the first step, fairly trivial step. Second step is to write the system. Let's call the system 1. So write 1 at each ti, so that will be dy by dt evaluated at ti, t equals ti is f of y of t equals ti and ti. Okay, that's what this is. So I've written it down at that point. Okay. The third step after this is make an approximation. Now this is where things become interesting, and there are lots of possibilities depending both on the equation you have at hand and what it is that you want at the end. Do you want something that's easy to implement? Do you want that it's something that is absolutely stable for all time steps? You know, these are considerations that you have to make. We'll come to that. But the idea is you make an approximation. Okay, what is the simplest approximation you can make? You can approximate the derivative. Okay, that's one way of doing this. So let's say this is, let me denote this. This is yi. Let's y at t equals ti is yi. Okay, I'm going to use that notation. So if I make an approximation for the derivative somehow, then I can in principle solve this for yi or yi and yi plus 1 or whatever. So simplest way to do that is, you've probably seen this maybe in a different form. If I write yi plus 1, that is y of ti plus h, okay, then I can open this in a Taylor series. That will be y of ti plus h times dy by dt at ti. Taylor series about ti, of course, plus terms that are what are called order of h square. Okay, this is called the big O notation. Big O, big. Okay, it means that if I take the limit of this term divided by h square, the limit of whatever this remainder thing is divided by h square, I'll get some number, some finite number, small number, reasonably close to 1, but okay, some number. It's not going to be 0 or infinity. Okay, so this is order of h square. Remember, h is the distance, the interval size. So the larger the interval size, the larger this is. The smaller the interval size, the smaller this is, because h square is larger than h. Okay, if the interval is large, right? So you want to have, you can only lower this if you make h smaller and smaller. Okay, so you want to keep that in mind. Okay, so if I do this, I will substitute that here. So step 3, substitute that. So I can substitute for dy by dt from here. Dy by dt at ti is y of ti plus h minus y of ti by h plus this term. Okay, and this term, if I divide by h, since its order of h square means, like I said, it's h square times some number whose details we are not interested in. This number is the second derivative of y evaluated at t equals ti, okay, divided by 2, whatever. So it's some h square times the number. If you divide this by h throughout, which is what I'm going to do, then this h will cancel with the h square and you will get something that is order of h. Okay, same number multiplied by h instead of h square, so it's order of h. Okay, so you will have step 3 continued. You will have dy by dt. Sorry, if I put it back in there, right? I have y of, and notice this is ti plus h is nothing but ti plus 1. Y that is yi plus 1. So let me just write it as yi plus 1 minus yi divided by h plus order of h. H is, that is this guy coming on the left hand side. This is f of yi comma ti. Okay, and so from here I can get a formula yi plus 1. This is, of course, you've probably seen this before. It's called the forward difference scheme. Okay, now let's not go, let's not jump there. Okay, so this, we have this is sort of like the forward difference scheme that you've probably seen multiple times before. The term that we have here, this is called the truncation error. Excuse me. Okay, and the reason it's called a truncation error is because you're taking a Taylor series and you're truncating it at this point. Okay, so the error that you're introducing is of the order of h. We'll talk about the error in a minute, but the smaller the h, the error goes down linearly with h. That's what that means. Okay, now I have everything here except for this term. Presumably y, I know, remember, right hand side you know what it is, right? So if I give it a yi at a particular ti, then I can calculate yi plus 1 from this equation, provided that this term is somehow taken care of. Okay, now notice that the reason that the truncation error is order of h square is because we dropped off in the Taylor series terms from second order and higher. D square y by dt square at ti and so on, we didn't take. Now you could in principle say, okay, maybe I can include those terms as well, but then you'll, if you take d square y by dt square, then you don't know over there what the term is going to give look like, and then what the additional terms are going to give you. Okay, because you will now have dy by, not just dy by dt at I, which is what you want here, but you will also have d square y by dt square at I, which is not here. Okay, so this is only written, this entire thing we still don't know what it is, we only know the right hand side, right? And so presumably you have to be able to evaluate this, but you can't get the second derivative. So you're restricted by that to be of order of h. Okay, so please keep that in mind. Good. Okay, so if you do this, then step number 4 is you drop the truncation term. So let's call this is tau ith step, so it's tau I, truncation error at the ith step. So you drop tau I and solve. So you get yi plus 1 is yi plus h times f of yi comma ti. Okay. So now you can start from ti t naught, which is 0. You know the value of y at t naught, y 0. So you put that into the equation, you will get y at t1 from here. Then you take that, put that back in here, you will get y at t2, continue, and so you will get an iterative scheme. You can solve for the y's at each of these time steps, each of these t values, not time steps, t values. Okay, and in principle, if you take more of these t values, you will get more values for y, so you can solve the problem. Okay, the final step is to check for stability. Now this is not a scheme we're going to discuss, this final step especially we're going to skip for now because it's a little bit involved. It's not terribly complicated, but so check stability of the scheme. Like I said, this is numerical stability, it's different from stability for fixed point in a differential equation. Idea is somewhat similar. You want to see if the scheme at any t gives you a value that is unbounded. So is it suddenly taking or eventually taking yi plus 1 before it reaches capital D, is it taking it to infinity? Okay, and if it does that, then the scheme is unstable. Okay, because it's making y artificially large. Now you can check if this is happening by computing the error. So let's say this is the actual solution y of t, and the computed solution is y of t evaluated at ti, and the computed solution is yi. Okay, the final computed solution. This is what you call the error, the actual solution minus solution that you calculated using this scheme. There is another contribution to this. This yi is actually what the computer gives you. So there is something called floating point error, which will also come in. But okay, we'll not worry about that for now. Okay, because the computer uses bits to represent a real number, and you don't know how many digits are actually relevant in the real number, so you can not go beyond the precision of the computer. But we'll assume that is good enough for us. Okay, so this error, if this error starts going towards infinity, or if the y itself starts going towards infinity, that's when error will go to infinity, then you know that it's unbounded. If it's not, for certain values of so if this goes for all h, then the scheme is unstable. And remember, this is a function not only of the h of the m you pick, but also of the original differential equation right hand side. So it depends on equation to equation. There's no general result saying that this is unstable or this is stable or whatever. And if it goes to infinity, or if it doesn't go to infinity, let's say it doesn't go to infinity. So if this is bounded for all h, then the scheme is stable. If this is bounded for some h, then it's called conditionally stable. Okay, so you have an unstable scheme, you can have a stable scheme, you can have a conditionally stable scheme. Okay, so that's basically what you do. So these are 5 steps, standard 5 steps that you will use. Now the difference between all the plethora of schemes that are there in practice today for solving initial value problems, differential equations. The details of all of those schemes vary only in this. Okay, they don't vary in, certainly they don't vary in 1. Okay, you can, 1 is just a way to pick, you can pick whatever you want. We've just picked for simplicity something like this. 2 is also fairly standard because you just write the differential equation down, add that particular Ti. But 3 is where you make the approximation, where you make this substitution for the derivative. In this case, this is a forward difference scheme. Okay, it turns out the forward difference scheme for most cases is only conditionally stable, and it's also what is called an explicit scheme. So if you look at this is called an explicit scheme, this particular approximation. The reason it's called explicit is because you can just directly start from 0 and just march forward, right? Your 0 comes here, you will get y1, y1 comes here, you get y2, so on. So you have an explicit formula for yi plus 1 in terms of the previous y's. So you can actually evaluate things quite easily. Okay. Okay, so now let's look at a few variations. So this is forward difference. Here you have seen this before. So let's see a few different variations of this, and then we'll see how to motivate some slightly more sophisticated methods. Okay, so that you don't just jump in and do forward difference every single time. Okay, that's the idea. Because it's not the best method. Remember, okay, forward difference we said forward difference, this was explicit, right, because it gave you yi plus 1 explicitly as a function of yi, and it was an order of k method. So remember the error that was there, that was an order of k. So if you plot the error, that y magnitude of yi, or y of ti minus yi, if you plot this on a log plot, this is the error. The error will go down, and this is the let's say the interval size h, or the inverse of the number of points. Okay, so h actually should be number of points. Let's make it number of points, m. Okay, so m is number of points. H reduces as you go from left to right. Okay, and the error will fall on a straight line in a log plot. So this is log. This is log. Okay, and so the error will go as order of k. Okay, so that is about the forward difference. Now we can make a few changes. So let's say what are the changes we can make. We can make changes in step 3. So let's call this 3a. So we change from the original 3 that gave us forward difference, and we'll make the following change. So we had dy by dt at, this was from step 2, ti is f of yi ti. This is from step 2. Now instead of using a Taylor series from ti plus 1 to from ti to ti plus 1, I'll write ty of ti minus 1. Okay, this is yi minus 1. This is y of ti minus h. Okay, and so this becomes again Taylor series y of ti yi minus h dy by dt at ti plus order of h square. Okay, again just like before. Just a simple change. Okay, instead of writing y of ti plus 1 in terms of opening Taylor series in yi, I am writing y of ti minus 1 in terms of Taylor series in yi. Okay, you will see what a big change this makes. So if I do this, I can write dy by dt. Sorry, this is dy by dt at ti. Okay, dy by dt at ti is yi minus 1, yi minus yi minus 1 divided by h, and plus a truncation term like we had last time, that's order of h. Okay, so by making this change, going from here to here, I have a term that is order of h. Remember, it was order of h square divided by h, that is going here. So I'm introducing a term that the remainder term that I'm throwing out of this equation is of order h. So it's linear in h. Okay. So if you do that here, the solution that you're going to, the set of equations that you're going to get, algebraic equations, is yi minus 1 by h. If I then do step number 4 and drop the tau I, f of yi ti. Okay. Now notice this is quite different from the previous case. So I now have yi is yi minus 1 plus h f of yi ti. Okay. This is very different from the forward difference scheme. This is like a backward difference scheme, you could think of it like that. You have probably seen this in some form. And this is very different because remember, you have to start from I equals 0. That's the initial value problem, right? T equals 0 is given to you, so you have to march it forward. So you know I0, from I0 you should get I1, from I1 you should get I2 and so on. So let's say if I take I equals 1, that means I have Y0 here. So I'll get y1 is equal to y0 plus h times f of y1 comma t1. So y1 is on the left hand side, it's also on the right hand side. So this is an implicit scheme. Of course, this f is known, so you can put that in directly, but it's still implicit. And in general, f is a nonlinear function. So to get yi, you have to solve a nonlinear equation. Okay, so if f then yi comes from a solve a nonlinear equation. Okay, nonlinear algebraic equation you have to solve to get yi in terms of yi minus 1 and ti. Okay, and so that's the reason this is an implicit scheme, and usually you solve a nonlinear equation using this Newton-Raphson type method, right? Some iterative scheme, some method to solve a nonlinear equation you can use to solve this. But the problem is you have to do this at every t, at every time step, so to speak, right? You have to do this I equals 0, you have to do this I equals 1, you do I equals 3, every time you have to do a nonlinear solver. Okay, and so this backward Euler is kind of cumbersome. This is called backward Euler. This, by the way, this is called, obviously, it's called forward Euler. It's more complicated to implement in the sense that it's cumbersome. If you have a very complicated nonlinearity, you have to solve a complex nonlinear equation. But the added advantage is that this is stable. It's an implicit scheme, but it's stable. And so in most cases absolutely stable. So you don't have to worry about taking very small time steps or very small h's. You can just directly go and do this type of solution. Okay, so that's another variant. So you have forward difference, this is like a backward difference. Okay, and that's another variant only in step number 3. Others are steps 1, 2, 4 and 5 are all the same. Okay, so that's another variation. Now you could think of another one where I do Taylor series for dy by dt in terms of yi plus 1, do Taylor's yi plus 1, and then another Taylor series like this in terms of yi minus 1, then add them up, I'll get what's called the central difference scheme. Okay, and that is not as stable as this or the other one. Okay, so you can make these variations and there are several possibilities. So all of these cases you're approximating for the derivative, right? You're approximating for this because the right hand side is known. Now there are another class of schemes which are slightly more clever, right? So far both of these, even central difference, whatever, anything you could cook up is basically a way to approximate the left hand side because the right hand side is known. Now there are another set of schemes, we'll call these 3b, where you do the following. Instead of solving this equation directly, you integrate this equation before you come to step number 2. Okay, remember this was at step 2. Okay, but even before you come to step number 2, you make a change. So you integrate this equation f of y comma t dt. So even before coming to step 2 where you actually ended up with this, you write this instead from step 1. Okay, if you do that, you can see why this is clever, because this gets rid of the derivative. So you now get y of t plus 1, ti plus 1, or let me just say yi plus 1, yi plus 1 minus yi directly from here. That's how it's defined, right? Yi plus 1, and this is just integral of ti to ti plus 1. And remember what we said in that hierarchy when we started, there was exact solution was better than series, quadrature was better than qualitative stuff, was better than numerical scheme. So the quadrature was up there, right? The fact that you could do an integral numerically and get a solution was considered to be quite good, because then this opens up quite a few possibilities for you to do. Okay, as I'll show you in a minute. So this scheme is presumably better than these schemes because it gives you some flexibility in how you evaluate the right hand side. Okay. Now notice f is a function of y, and y is what you're trying to determine. So you really can't get, this is just a symbolic thing more than anything else, right? But you can do one thing. You can approximate this as opposed to approximating this in step number 3. And usually this leads to a better scheme. Okay, I'll give you a couple of examples. So if you use the trapezoidal rule for evaluating the integral, again, if ti plus 1 and ti are close enough, you can use the trapezoidal rule. And I'll show you why this is a better scheme. Okay, if you remember the trapezoidal rule, it looks like this. yi plus 1 comma ti plus 1 plus f of yi comma ti plus order of h cube. Okay, that's what the trapezoidal rule is. Okay, this tells you a way to evaluate the area under this curve using the values of the function at the endpoints of the curve. Okay, so what you're doing is, when you're doing this approximation, you have, let's say, f as a function of t like this, hypothetically. Okay, remember y is also a function of t, so f can be written as a function of t in the end if you knew what y of t was. So what you're doing now is you're trying to evaluate the area under this curve, and you can do that by doing various approximations. You could do this, approximate the entire thing as a rectangle, that's called the right box. You can approximate the entire thing as a rectangle here, it's called the left box. You can approximate using trapezoidal rule, taking the average and so on. Okay, so you can do that. So that's basically what all of these schemes will do, but we'll use this formula for now. Okay, now notice also that this remainder term is order of h cube. Okay, so if you put it back in here, you will get yi plus 1 minus yi. If I divide by h, remember this was what I was doing in the previous, in these two schemes on the left hand side, this the yi minus 1, whatever, then I will get 1 by 2 yi plus 1 ti plus 1 plus okay plus order of h square. Okay, so now the truncation error is order of h square. So this has become a higher order scheme than these, right? These were order of k, so these were lower order schemes. Now this is order of k square. So if k is a small time step, right, between the two ti and ti plus 1, okay, sorry, h, not k, h. So h is the time step between ti and ti plus 1, and if this is order of h, that means the error is proportional to h. in some sense. This is order of h square, so that is a higher order. So this is a higher order scheme than that. Okay, that's how you talk about an order of a scheme. Good. Okay. So now again I have yi plus 1, I have yi, I have to start from I equal to 0, let's say, and I'm going to go out. But yi plus 1 also appears on the right hand side here, also appears on the left hand side, and so this is also an implicit scheme. Okay, so this is called the trapezoidal scheme. This is also implicit, just like backward order, right? Backward difference, backward order, those are also implicit. But its advantages over this in that the error is smaller, the truncation error is smaller. Okay. Good. Now there is one more variant I will discuss, and then we will call it a day, which is the following. Let me keep this final formula down so that we can use it for inspiration. Okay. Now notice this, even though this is order of h square, it is still implicit, so it's kind of painful to implement. So what we want to do now, which is let's say 3c, is we want to ask the question, okay, I know that the y excuse me, yi plus 1 minus yi by h, this looks, if I compare it to the differential equation, dy by dt, right? This original differential equation evaluated at I, Ti. This looks like I've taken the left hand side, but the right hand side I am sampling at multiple points. One point is yi, the other point is yi plus 1, Ti plus 1. Okay. So the question that we can now, and this gave me advantageous things because the error was order of k square, and it was stable. So this is also a stable scheme. Okay. So the question that you want to ask now is, can I generalize this idea where I am taking multiple values of f sampled at different point locations and then add them up and get some way of evaluating this at the end? Okay, that's what I want to ask. Okay, and so if I do that, then let me write down just purely by inspiration from here an expression that looks like this. So I h, sorry, not k, h. So h goes to this side. I'll get rid of the by 2 and then I will generalize this to a times f of yi plus b times f of yi plus some number, let's call it alpha k f, okay, I, and Ti plus beta k, beta h, sorry, h. No, I keep saying k. Okay. So I've taken Ti plus beta times h. Okay, I've generalized this. This is sampling from one point y to the next point, I plus 1, Ti plus 1 yi plus 1. But instead of this, I say, okay, I'm going to sample it at a slightly different point. I don't know alpha, I don't know beta, they're unknowns. Okay, I don't know A, I don't know B, they're also unknowns. So just like I had equal weights to f and f here, I'm going to do this and then I'm going to see how do I get alpha and beta such that this entire thing forms a good approximation for the left hand side. Okay. So just by analogy, I've just generalized this 1 and this 1 coefficient to a and b, and I've generalized I plus 1 to some alpha hf, right, and beta h. It's fine. If beta was 1, then this will be Ti plus 1. If alpha was, well, 1, then this is an approximation for yi plus 1. It's not equal, but it's an approximation. Okay. Good. Now what do I do? Well, I can write down the left hand side just like I did before. This is y of I is Ti plus h, right? And this is y of Ti plus dy by dt at Ti, and dy by dt at Ti is f, right? That's the differential equation. So that's f at y at Ti times h plus the second derivative, that is h square by 2. This is h, yeah, y double prime at Ti. Okay, so that's what the left hand side is. So I can already cancel this guy and this guy. Okay, and then I'll have order of h cube, order of h cube. So then if I put this on the left hand side, I'll have f of y I Ti times h plus h square by 2. Now y double prime of Ti is d by dt of dy by dt, and dy by dt is f, so this is d by dt of f. And remember, this is the total derivative of f. F depends on t directly by itself, and it depends on t through y. So I'll use the chain rule. So this will be dou f by dou t plus dou f dou y times dy by dt, that is again f. All of this evaluated at Ti. Okay, because y double prime at Ti. So I'll get h square times, let's just use shorthand for this. This is ft, this is fy. Okay, so fy plus ft plus order of h cube. That's the left hand side. Okay, now the right hand side, I can open this guy in a Taylor series again, but now this is Taylor series in two variables. Okay, and this is LHS. I'll open the RHS. RHS, remember this guy is gone. So the first term I have is h times a times f of y I Ti, plus I'll open this guy, this entire fellow up, about y I Ti. Okay, again Taylor series, and that will give me hb f of y I Ti. Okay, plus actually b also can come out. This will be dou f by dou y at I times the difference, that is alpha h f. Okay, difference between this and yi, that is just this, plus dou f dou t at I times beta h plus order of h square. Okay, whatever those terms are, doesn't matter. Okay, now I can compare terms order by order. So the order of h term on the left must equal the order of h term on the right. The order of h square term on the left must equal the order of h square term on the right. The order of h cube term, and so on. Okay, so if I just compare the first one, so order of h term, then I'm going to get f of yi comma, this is the only order of h term on the left. On the right side I have two order of h terms, this plus this. So I'll get f of yi Ti is common to all three of them, this one, this one, this one, so it will cancel out. So I will get a plus b equals 1. Okay, that's order of h. The order of h square term, which is next, is this on the left hand side, ft plus ffy, and this on the right hand side with the hb outside. Right? Okay. So if I evaluate terms that are multiplied by h square on both sides, this is the left, this is the left hand side, this is the right hand side, then I will get b times alpha, h square is outside, b times alpha is half, and I will get b times beta is half. So I will get alpha equals beta, and I will get 2 alpha b or 2 beta b, doesn't matter, is equal to 1. Okay, so I have 3 conditions. These are called the order conditions. Okay, and 2 alpha b is equal to 1. Okay, so I have 3 conditions, 3 order conditions, but I have 4 unknowns. A, B, alpha, beta. Remember, I don't know what any of them are, right? So I can pick one of them, I have the freedom to pick one of them, and I can pick them in such a way that the scheme becomes easy to implement, depending on the way f looks, depending on the non-linearity that is there in f and so on. Or I can pick them so that the stability is ensured under the conditions I'm interested in, or you get region of maximum stability. I won't tell you how to do that, but it can be done. So I have this additional constraint that I can impose by myself to get unique values of A, B, alpha and beta. Okay, but the logic of the scheme is this. You have these points unknown a priori where you are picking values and then you are trying to see. Now, why are we doing this stuff? Why are we doing this stuff? We are doing this stuff because when you expand on the left hand side, when you take the derivative yi plus 1 minus yi divided by h on the left hand side, the highest order term, when you divide this by h, the term that you are dropping off is order of h square. Okay, that is point number 1. So, this truncation error is order of h square again. Not only that, the scheme now, if you look at it, the scheme that you have over here can actually be made explicit. Okay, why is that? Because you now take the right hand side and you evaluate it at a given point, okay, which is determined a priori, and then you use that, put it in, get yi plus 1. Remember, this is not yi plus 1 on the right hand side. Okay, so you can make this an explicit scheme. So these, this is basically part of a big family of schemes. They're called the Duns-Scotus schemes, or RK schemes. And this RK scheme, this particular RK scheme, is of order of h square. So it's accurate up to second order in h. So it's called an RK2 scheme. So this entire enterprise, once you fix the other constant, is called an RK2 scheme. Okay. Now you can imagine adding more points like A, B and C, alpha, beta, gamma, delta, and then increasing the number of sampling points and so on, and you can get a higher order scheme from there. So you have something called an RK4 scheme. Okay, so RK4 is the most common. If you go to MATLAB or Python or something, you will see that RK4 is the most commonly implemented scheme because it's stable over a wide range of h values and for various systems. Okay, so it makes sense to use it. But that's basically the logic of where they come from. Now, I don't expect you to remember any of this stuff, but you should know loosely where these ideas come from and what they're useful for. Okay, so you have the RK family. Okay, so these are basically the different types of schemes that you can use for solving an initial value problem. Okay, and usually the trapezoid, the integration based schemes, the quadrature based schemes that I talked about, those are somewhat more flexible because you can approximate that integral on the right hand side by anything. So you can take the values at the 2 points, you can have an interpolating function between the values, you can do a whole bunch of things with the integration based scheme. So that's usually the most versatile of the lot. So these are the most standard that you've probably seen before. This is probably the most versatile, and this one is probably explicit, so it's easier to implement compared to those. Okay. Good. Okay. So that basically tells you everything about numerical schemes for IVPs, at least an introduction of numerical schemes. What are the basic things to look for, the 5-step procedure and so on, so that if you're interested and you eventually decide to take up a more serious study of these schemes, you can use this hopefully as a starting point. Okay. Now the final thing that I wanted to mention is thing about boundary value problems. So in BVPs, you will see that, for example, for boundary value problems, you will see, for instance, that if I have a system, okay, dy by dt, like this, and then I say y bar at 0, or some y bar at 0. So let's say y0, y1 at 0 is equal to a, y1 at t is equal to b. Okay, this is a boundary value problem. And the problem with solving these is, if you think just in terms of the, let's say only the one of the finite difference schemes. So let's take the simplest one, the forward Euler, okay, the forward difference scheme, plus h times f of, okay, this was the simplest one we started off with, the simplest one that you can probably come up with here without worrying about the initial conditions, remember. Now this was for a 1D system. When you have a 2D system, you will have two equations like this. So you will have yi plus 1 for y, let me now make this a superscript, I plus 1, y1, I plus 1, y1 I, f1, y bar, whatever, t, okay. So then y2, I plus 1. Okay, remember this is a 2D system. Boundary value problems, the distinction between IVP and BVP becomes non-trivial only when you have second order and higher. We've discussed this before. So this system is this system. Okay, same whatever we've discussed has just been extended to this case. Okay, now you know how to solve this because you know t. You can start from t equals 0. You can just start and go. Not quite, right? Why is that? Because of this. So if I wanted to time step this, step this up from t equals 0, I'll need the y at t equals 0. And remember, this y bar is y1, y2. So which means I'll need y2 at t equals 0, but I don't have y2 at t equals 0. I only have y1 at t equals 0, and I have y1 at t equals capital T. Okay, so already you see that even the most simplest technique that we could cook up for an initial value problem will not work for a boundary value problem. Okay. And that's the reason why these are a little bit more complicated to work out. So usually you have to do something called a shooting method. That's the simplest boundary value problem solver you can do. So you assume some value of y2 of 0, okay, and then you solve the solution all the way up to capital T, and then you see the difference in whatever you have computed and the actual boundary condition that should be there at capital T. Okay, and then based on that you change the initial guess for this. You shoot again, go to capital T, check the error, come back, shoot, go, and so on. So this is called a shooting method. It's the simplest way you can do this, right? But then the stability of these schemes are highly non-trivial, and so very quickly you will realize if you have some complicated right-hand side that these schemes can become unstable or can be extremely cumbersome. So you keep shooting and trying, you will never really reach the final solution to within some bound. So boundary value problems need a more complicated, more subtle treatment, and so you will have to look at some alternative techniques for solving them. Okay, so we won't go into the detail, but it's just something that tells you how and why the complication comes from. Okay, so with that, we're basically done with what we started out to do, I suppose. Let me summarize quickly. Again, I'll go back to the diagram of increasing hopelessness, and hopefully you have now some hope of solving some of these problems and not just despair, or at least somewhere where to start, right? It's not a complete black hole. So for instance, we said that you need exact solutions or closed form solutions. That was the first, and then the next one, I think it's only pertinent to end with this since we started with this and I've been saying this right along. Series quadrature, okay, and then the next one was qualitative methods, and the final one is numerics. Okay, and still the aim is always to try and get some exact solution, some functional form. Something goes like sine square t, something goes like sine sine t e to the power minus t, something like that, right? That's always better because it gives you some idea of how the function behaves in the vicinity, especially of a large, some domain t large, t small, whatever. So you could combine these two eventually, if this is like a next course, this is what you will probably do, and look at what are called perturbation methods or asymptotic methods. Okay. So this will tell you things about the solution. This especially will tell you things about the functional form of the solution, let's say for large t. So if you were solving, let's say PDE, and then you ended up with a Bessel function, and then some bizarre looking Bessel function, let's say, and then you wanted to know what that function looked like for large r. Does it decay? Does it grow? Things like that. Or even the functional form. What does it go like? Does it go like e to the power of minus t? Does it go like e to the power of plus t? Does it go like sine square t per t? Does it go like cos t by t? Whatever. Okay. So those are things you can do when you do asymptotic series, asymptotic expansions. Okay, that would be a logical next step for you to continue from here, from where we have stopped. The next logical step will be to combine this and say something about bifurcations in higher order systems. Okay, just like you had fixed points in a 1D system, and I also briefly mentioned that you can have limit cycles in a 2D system. We didn't discuss that. And then I said there are things called Hopf bifurcations where fixed point can interact with a limit cycle as you change a parameter and so on. So that becomes important. Those types of bifurcations become important in 2D. When you go to higher order systems, you can have even more strange, if I may use the word, fixed point analogs. So you can have fixed points, you can have limit cycles, you can have things called strange attractors. Okay, and these are points where the trajectory appears to come to them, it circulates around them, but then it leaves him at the end. Okay, this never happens in 2D, it happens only in 3D, and that is the basis for what is called chaotic dynamics. But that's a whole new zoo of things that you can study based on bifurcations. Okay, and a combination of these two usually appears in what is called stability analysis. Of PDEs. So if you have a system that shows certain spatial and temporal, it has certain time and space dependence, spatio-temporal dependence, then you can start looking, using many of these techniques, you can start looking at stability of certain solutions. So are there certain wavelengths that are unstable, for instance? Are there certain frequencies that appear at certain wavelengths and things like that? Okay, so you can start saying stuff using these ideas. And of course, numerics by itself is a massive area. It's not an area I work in personally, but it is an area that there is a lot of expertise, especially in our department. There are lots of people working on numerical schemes for ODEs and PDEs, and so that's another area. So you could, for example, for the analog of the quadrature type scheme would be like a weak form of a solution in elasticity, which is the basis for finite element techniques. And so you could start extending some of these ideas to some of those problems as well. Okay, so things like finite element methods, CFD, and so on. Okay, so I hope that gives you a broad picture of the world of differential equations. Of course, like probably indicated here, it's much bigger than what we've been able to discuss in these 10 or 11 sessions, and the hope is that whatever you have picked up from here should give you a good basis on which you can build some of these additional structures and learn a little bit more about some of these specific techniques and so on. Okay, so we'll stop with that for this part on differential equations.